Today we will wrap up the module on divide and conquer, and more specifically I just will review where we were with the selection problem, and then we will go over a new problem and a very interesting algorithm for this, and it's a really fun problem to I really enjoy presenting this problem in class because you can think about lots of interesting questions there, and it's a relatively standard divide and conquer, but it gives rise to interesting recurrences. So we'll see all of that in the closest pair problem. And then next class onward, the next class will be a review of elementary data structures. Okay. Just logistics. Your problem set 2 is due tomorrow, and problem set 3 will be posted sometime tomorrow or early Thursday at the latest. And problem set 3 will cover more divide and conquer, and it might cover data structures that we're going to plan to cover on Tuesday, depending upon what we do. Okay. One note about submission of problem set 2. I think most people submitted things correctly, but there were a very small number of students who did not submit typed answers. There were some students who submitted handwritten answers, and I think as we have indicated very clearly, all your solutions should be using a word processor. It doesn't matter what you use, Word doc, Word, LaTeX or text is fine. For certain pictures, you can certainly draw them by yourself, fine. The second request is please submit either Word doc files or PDFs. Don't submit zip files. Don't submit LaTeX sources. Just the final output, which is either a PDF, text, or Word doc. Okay, so let's just remind ourselves what we have done so far in divide and conquer in general. So we started talking about sorting, and we recognized that sorting can be done in theta n log n time. There is a simple algorithm called merge sort that completes the sorting in n log n time. You have seen other sorting algorithms. Many of you have seen other sorting algorithms in the past. The classic ones are merge sort and quick sort and heap sort. These are three algorithms that are often used for sorting. It doesn't matter for our purposes as we go along. If ever we need to use a sorting routine, we would be fine in principle in using any one of these. Some things you should remember. A merge sort has a worst case bound of theta and log n. Heap sort also has a worst case bound of theta and log n. We haven't seen heap sort in class, but something you can remember. quicksort is one of those algorithms like little bit like the randomized version of selection. Its worst case performance is not n. Its worst case performance is actually n squared. But the randomized version is worse than theta and log n time with very good probability. And in fact, in practice, it outperforms for many scenarios. It outperforms both Mozart and beta. Okay. In fact, the sort routine in most of the operating systems that you often use, you might invoke, just uses quicksort. But for our purposes, if you have an algorithm that where you need to do sorting, you can just say sort using your favorite sorting routine, and that will be fine. And you can go ahead and assume that that takes that long. Okay. One thing we did not go over, which actually maybe we will go over later on, is the fact that it turns out that if you only allow algorithms for sorting that compare elements, that do not do any fancy computations like addition of numbers or multiplication, if all you're allowed to do is comparison, it turns out any algorithm requires omega and log n. Okay, this is a remarkable result actually, and it's a result I think that is different from anything else you might have seen, in the sense that this is a statement about every algorithm. This is not a statement about, this is not the analysis of a particular procedure. This is a statement that no matter what you do, if you want to sort, and if you want to sort an element, if you have a sorting algorithm that works for all possible inputs, there will be some input for which it will end up taking omega and log n time. Effectively meaning that these routines we have developed are the best possible if you don't worry about the constants that we are dropping when we go from the theta to when we go with the Sisson multiplication. Okay? So so that's a very satisfying statement, because you go ahead and develop some algorithms and you find that you can't really do better than that, other than maybe some kind of engineering in trying to improve the performance for a given input, for a given collection of inputs. So in that sense, the sorting problem is completely well understood. Okay? In this setting, so I should clarify that this is not for any algorithm. This is for any algorithm that does sorting by comparisons. Okay? You might have heard of things like bucket sort, which take the question again. You might have heard of things like bucket sort that apparently complete sorting in linear time. Okay? Those are very specific kinds of sorting routines that do not work for all kinds of elements. They only work for numbers. They only work for numbers within a certain range. So those do not fall in this category. This is the most general purpose sorting procedures that can sort anything that can be compared. Yes?
You said that any sorting algorithm which will compare elements
will
have n log n time, like omega of n log n.
At least omega. Yeah.
Okay.
At least. That's the point. Any algorithm will take, of course you can come up with absolutely slow algorithms, right? There is no. So, but any algorithm, however fast it claims to be, it needs to take at least this much time on some input. Okay? Okay, so that is as far as sorting is concerned. Then we looked at the problem of selection, which is sort of similar to, has a similar flavor to sorting, but remember, the focus here is not on sorting the entire input, it's on finding an element of a certain rank, for example, the median, or the 25th percentile, or the 47th percentile, or something like that. And there we saw two algorithms, a randomized selection and a deterministic selection. And remember, the deterministic selection algorithm this is the one that makes two recursive calls. This is the median of medians algorithm. Sometimes that's what it's called. This algorithm we showed takes theta n time. This algorithm, we haven't analyzed it. We said, oh, most of the time it seems to be doing well. That's all we. So we will. I will present the recurrence for this. We won't prove it because it will take some time to prove it, but it can be proved without too much of a puzzle. So we will show that its running time. When it's a randomized algorithm, we often look at expected running time. Expected time will also be that. Okay? Once we have developed an algorithm for a problem, like selection and so on, and if ever you need to use selection, if ever your algorithm or your subroutine invokes selection, you don't have to go ahead and prove any of this. You can just say, oh, I'm just going to use the selection algorithm we covered in class or in this book or whatever, and that's going to take care of it. Okay? Okay. So let me remind you about the randomized algorithm. The randomized algorithm basically was, if you had to, and I'm going to just write a very, very high level overview. I'm not going to go over the detailed pseudocode here. So the basic idea was pick a random pivot, partition around the pivot, pickers in appropriate on appropriate side. Is this clear to everybody? It should, even though it's a little cryptic, but I'm assuming everybody understands the context here. What's going on? Yes.
I just want to verify that during the position stage, you're sorting the left and right.
Not sorting.
Okay, so what exactly is it?
Partition. Very good. So partition, that's very important. So it's a good question. We don't want to sort, because if you sort the, let's say, if you were to sort the first half, okay? Let's say you decide that you're going to sort the first half, then here is a claim that any algorithm in the worst case might take as long as n log n. Of course, here now n is half of n, but that's still a good portion of it. So we don't want to sort. Partition basically means all you're going to do is, if this is your array, okay, this is your array. You're going to pick a random pivot. Let me pick 9 as my random pivot. I'm going to put everything less than 9 on one side, everything bigger than 9 on the other side. But I don't care how they appear, in what order they appear. Okay? So what we will do is we will walk through this. So is it less? Yes. Is this less? Yes. Now I'll leave this here. Is this more? Less or more? It's more. So I want to put it on the other side. So let's imagine I'm filling it from here. 6 is less. 7 is less. 93 is more. 11 is more. 12 is more. So this is one way to partition it. And the key thing is the partitioning should take only linear time. Okay? Okay, so now how do we write the recurrence for this? The problem is this was the random pivot. And we went through a lot of examples, right? Okay, what happens if you get it half-half? What happens if you get it 3/4, 2/4, 1/4, and so on. So I'm going to write down a recurrence which captures what is going on. It's not going to be very precise, but you should be able to get the idea of what's going on. So I'm going to say if Tn is the expected time on any input. So I want to place a bound on how large Tn can be. So Tn can be the following. Okay, I certainly need to take a linear time for the partition. Okay, let me just write that down as n. In reality, it might take something like 2n or 3n, it doesn't matter, but that constant will just come out everywhere, so I'm going to just write down n. After this, how much time it takes depends upon what the appropriate size is, right? Agree? What about the appropriate size? We saw this, that now we don't have any control whether it's going to the smaller side or the larger side. Which side it goes to depends upon the value of the rank that we are trying to select. Remember, we are asked to select a particular rank, right? So we don't have a, so let's always assume it goes on the larger side. Okay? So we went through this calculation. What is the probability that the larger side is, so the larger side can be between roughly n over 2 to n minus 1. And it's equally likely to be any one of these numbers, right? So there are n over 2 numbers like this. So each will have a probability of 2 over n. Okay, roughly speaking. So you get the probability 2 over n. It goes into the larger side of the size n over 2. With probability 2 over n, the larger side is of size n over 2 plus 1. With probability 2 over n, the largest side is of size n over 2 plus 2. And with probability 2 over n, the largest side is of size n. Okay. Now this is not completely precise, and here is the reason. And I think if I could try to be very precise by saying the following. Notice that with some probability I will actually find the pivot element itself will be the element that I'm looking for. What's the probability that the pivot element is the element that I'm looking for? 1 by n. So I should actually, technically speaking, subtract that probability from this. So this is sort of an over, it's a valid bound, but I could be smarter and I could do a better job of it. Okay. Now that's a recurrence we have never seen. And in fact, none of our techniques that we have employed of building this recursion tree will not work here, right? Because remember, at a recursion tree, we would have a node at the top and we would have a fixed number of children. But here, the number of children is a function of n, right? So this would be too complicated to put in the recursion tree. Okay? Is there any questions about the recurrence before I say something more?
Can you just explain me about the factor 2 by n?
Good. When you get the factor 2 by n. Okay. So remember that we have here are the possibilities 1 and n minus 1. So I'm drawing one side, the one side here and the other side. Okay. So let's say this is the left side, this is the right side. So the left side could be 1 and n minus n, n minus 1, 2 and n minus 2, 3 and n minus 3, n minus 1 and 1. Okay? Actually, this is also not very precise, if people see that, because this is one, we are setting aside the pivot, so this should be 1 and n minus 2 or 0 and n minus 1. So, okay, maybe let me be precise there. I should say 0 and n minus 1. So I do 0 and n minus 1, 1 and n minus 2, 2 and n minus 3, n minus 1 and 0. Okay, so this is the left side, this is the right side. I am always assuming that I'm going to the bigger side because I don't have any control on what is. So the largest side here is n minus 1, n minus 2, n minus 1, n minus 2, n minus 3, and in the middle we have n over 2. Okay? Each of these is equally likely. Okay? So what is the likelihood of the side I'm recursing on being n minus 1? 2 out of the number of options here. So 2 out of n minus 1. Do you agree? 2 out of n minus 1. Similarly, n minus 2 has 2 out of n minus 2. So that's what this corresponds to. Okay, and since I went through this calculation, if you really want to me to get this precisely right, I will write this as 2 over n minus 1. Okay? Any other questions about this reference? Okay, yes?
N by 2 we have only one of
Well, it depends upon whether n by 2 is even or odd. Right? It depends upon n is even or odd. In some cases you will get actually 2 choices, in some cases you. Yeah. Okay, so that's why really, and if you have to be very precise, this is really may not even, if n is odd, then this is not even a valid integer, so you'll have to put floors and ceilings here. So that's the right way to do it. Okay, but here I'm just going to give you a feel for what's going on here. So based on our intuition that, oh, most of the time, if this is the split, then this would take a long time. If this is the split, then it will take a long time. But the vast majority of the time, we get a recurrence that we know the contributions decrease geometrically over number of levels. We went through this. We went through with 3/4 n, we went through with 9/10 n, we went through with 99 over 100 n, and so on. So most of the time it seems to take linear time. So let me guess that this is linear time. Okay? And see whether we can prove it. So guess that T of n is less than or equal to C times n. For some C, for some choice of C. For all n. Okay? Now how do you go about proving this? So suppose this is my guess, so I want to prove this. How would you go about proving this? Induction. Okay? You would say, alright, let me assume that this statement is true for every n until a certain point. Let me prove it for the n after that point. Okay? So first we will do the base case. The base case will be for small n, when n is only, here in this piece of code, I have not specified the base case, but the base case is very standard. You can take a base case to be n equals 1, 2, some small number. You agree that in that situation, the time taken would be less than or equal to some constant times n, right? Because the base case is just constant amount of time, so your C can be made appropriately large. So base case is trivial. So what about induction step? Let's try that. Suppose T of n is less than or equal to n plus 2 times T of 2 over n minus 1 times Tn over 2 plus Tn over 2 plus 1 plus T of n minus 1 for all n less than n. Okay? Now I want to prove the same thing for T of n equals m. So need to prove for n equals m. Okay? Okay, so let's try to prove it. And even though it seems daunting, it's actually, you just work through the steps of it systematically, you will get what you want. So what do we need to prove? What does it mean that I need to prove for n equals m? What statement do I need to prove? What's the left-hand side of the statement that I need to prove? T of m. So my goal is to prove T of m. What's the right-hand side of the statement? Exactly the same thing with n replaced by m. This is what I need to prove. So let me write that out. Okay? That is what I have to prove. So I have to start, let's say, from my left-hand side. And, sorry. I'm making a big mistake here. This is what I want to prove. This is what I want to prove. This already, I already know from my recurrence. Okay? So suppose, so my induction step is, suppose T of n is less than equal to Cn for all n less than equal to less than n. That's the statement, right? T of n is less than equal to Cn for all n less than n. Okay? Need to prove for n equals m. That means what do I need to prove? I need to prove that. So this I already know. This is what my recurrence already says. T of m is less than equal to this. What do I need to prove? I need to prove this statement for n equals m. So what's that statement? T of m is less than equal to C times n. This is what I want to prove. This is what I know. So I want to go from here to here. Okay? So my left hand side is already the right one. So I need to somehow manipulate this to arrive at Cm. Okay? So let's see what I can do. Of course, when I'm trying to prove this statement, and this is by induction, I need to use my induction hypothesis. Right? Does my induction hypothesis apply to this? T of m over 2? Yes. Why is that? Because m over 2 is strictly less than m. Right? And I said that my statement is true for all n less than m. So by induction hypothesis, T of m over 2 is at most C times m over 2. So I'm going to put a less than equal to here. C times m over 2. By induction hypothesis, T of m over 2 plus 1 is less than equal to C times m over 2 plus 1. And by induction hypothesis, T of m minus 1, does that apply to the T of m minus 1? Yes, because it applies to all n less than m. So it applies to m minus 1 as well. So T of m minus 1 is less than equal to C times m minus 1. Okay, so this whole step is where we apply induction hypothesis. Clear? Okay, so now you realize that all we have to do is algebra at this point, because there is no t on the right hand side. All we have is a bunch of numbers that we have to add, and what we have to show that this whole thing is less than equal to C times m. Okay? Let's try to see. Notice that we have the luxury of choosing our C, okay? Because we didn't specify it. We just said let's hold off on specifying the C. But remember, we're not going to change the C from one induction step to another induction step. We'll always use the same C. but we can choose it so that it works for all cases. Okay, so what do we do here? We take the C out. Okay, and what are we left here? M over 2 all the way till m minus 1. You recognize that this is the sum of consecutive numbers, right? M over 2, M over 2 plus 1 and so on. So this is an arithmetic series, so you could use the formula for arithmetic series, or you could use the formula you might know for adding the first x numbers and then subtracting the first x over 2 numbers. Something like that. So let's try to write it like that. So this summation I'm going to write this out as 1 all the way till n minus 1. Okay? Minus 1 all the way till n by 2 minus 1. So I'm removing the first, it's the sum of the first n minus, not n. First m minus 1 numbers minus the sum of the first m over 2 minus 1. Okay? So this is equal to m plus 2c over m minus 1. What is this? 1 through all the way till m minus 1. M times m minus 1 by 2. What's that? M over 2 times m over 2 minus 1. Okay? Okay, so let's keep going. This is m squared, so let's take the 2 out. So that 2 cancels with this 2. So we are left with c over m minus 1. What is this? M squared minus m. And what will this be? So this 2 is gone. So what will this be? M squared over 4 minus m over 2. Okay? Okay, so what does that come out to? 3m squared over 4 minus m over 2. So let me write that out here. Right hand side, I'm just operating on the right hand side. So m plus c over m minus 1. M squared, so 3m squared over 4 minus m over 2. Okay? Now, when you see all these calculations, it can seem again there are too many terms going on, but let's try to just intuitively see what's going on. Okay? So we want to, what do we want to show? That this quantity is less than equal to? No, not c times n. That's what we want to show. At the end, we should be able to get c times n. Okay? So we have an n here. So notice that here, among these two quantities, which is the dominant quantity? M squared. And in sort of, this is much bigger. For large values of m, this is like very tiny. Okay? And it's not clear whether, in fact, when you multiply by 1 over m minus 1, that's basically close to a half, right? So I can completely even ignore this, because I can simply say this is less than equal to m plus c times c by m minus 1 times 3 by 4 m squared. You agree? Going from here to here, right? Because I removed the negatives. Okay, good. So what about this? This is an m minus 1. If let's imagine that this was simply m for now. Okay. Then what would this be? 3 over 4c. Right? 3, and there is another m here. So let me actually do the calculation without the minus 1 for now. Okay? So this is not quite right, but so what do we get? M plus 3c m over 4. Okay? What is this? M times 1 plus 3c over 4. So when will this statement be true?
C is
If-
larger than 1
if-
plus 3c over 4.
Okay, so this will be true if 1 plus 3c over 4 is less than or equal to c, which is the same thing as c at least 4. So this whole statement would be correct as long as c is bigger than or equal to 4. The only caveat was this was actually m minus 1. And when I replaced by m, I was actually going in the wrong direction. Okay? There are various ways, if we didn't care about the constant c, there are various ways of fixing it. I could say that, oh, m minus 1 is always at least m over 2. Right? And m is sufficiently large, when m is bigger than 2, m minus 1 is always at least m over 2. So I could replace this m by m over 2, and I could say that this is less than or equal to m plus 2c over m times 3m squared over 4. I could go from here to here. If I do that, then instead of 3c over 4, what do I get? 3c over 2. But that would be a problem. You see why that would be a problem? Because then we are trying to argue that 1 plus 3c over 2 is at most c, which is certainly not true. So this is too bad an approximation, so we should not do that. So this won't work. Okay, but you can put anything that is smaller than 3 over 4. Basically, any time you can say that, oh, m minus 1 is at least 9m over 10. And when we do that, we can get a different value of c. Let me just show you one thing, just so that you see how to argue when you need to make it formal. So, let's see. So let's do it slightly differently. So let's say I write this as I take out m, and I get 1 plus 3c over 4 times m over m minus 1. Right? You see that? I take an m out, 1 plus 3c over 4 times m over m minus 1, one of the answers comes. Okay? So we want this to be smaller than or equal to c. We want this to be smaller than or equal to c. Okay. What happens to m over m minus 1 as m goes large? It's going towards 1. Okay? So that's why I was ignoring it. I was saying, oh, let's just ignore it. But if you had to be precise, you could say, all right, at some point, and one observation was that it's always at least half, but that is not enough, because if you put a half, you get a 3c over 2, which is bigger than c, so that isn't good. But at some point, it's always bigger than, instead of a half, after some time it will be bigger than 2/3, after some time it will be bigger than 3/4, after some time it will be bigger than 4/5. You name whatever it is. Right? So you could say that as m increases, for m greater than or equal to let's say 10, n over m minus 1 is at most 10 over 9. Okay? You agree with that? So as long as n is greater than or equal to 10, m over m minus 1 is less than or equal to 10 over 9. So I'm going to replace this by m times 1 plus 3c over 4 times 10 over 9. So I get these two, so then I get 5, so I get 5c over 6. 1 plus 5c over 6. We want this to be less than c times m, which will be true as long as c is at least okay. So as long as m is greater than or equal to 10 and c is greater than or equal to 6, I can make this argument. So I can choose my base case to be something like m equals 10. When the size of the array is small, I know that it's going to just do a constant amount of work. So I can prove that T of n is less than or equal to c times n for all n greater than or equal to 10, or for all n by choosing my c such that it's at least 6, and at least a value chosen so that the base case holds. Okay. C chosen such that okay. Yes.
I got lost on the far right side. As soon as you, like right at the bottom of the right, how we went from the one above it to down below.
Okay. How did we go from here to here? So this is just the sum of numbers from, let's say m was 100. So this is the sum of numbers from 50, 51, 52, 53 till 99.
Okay.
So I'm saying that the sum of the numbers 50 plus 51 all the way till 99 is the same as adding 1 through 99 and subtracting 1 through 49.
Okay.
Do you agree? The sum of numbers 50 through 99 is the same as adding the numbers 1 through 99 and subtracting 1 through 49. Okay? So think about it. And why are we doing it? Because we know that there is a formula for 1 through 99. The formula for 1 through 99 is 99 times 100 by 2. N times n plus 1 by 2. Okay? So that's what we put in here. It's m times n minus 1 by 2. Here we put in this times it plus 1 by 2. And then this is just algebra. We just go through this. Okay, so that's how we get this. This is exactly the same as this. This is just a simplification. This part, we went from here to here by making an approximation. We replaced the m minus 1 by n. Okay, and then we got this. All this part was trying to say, okay, what if I don't allow you that approximation? How do I go about arguing? Any other questions? Yes.
Couldn't we prove that the third line that is less than equal to p by n? And we could assume that m by 2 is less than equal to m minus 1. Similarly, m by 2 plus 1 is equal to less than equal to m minus 1. Similarly, all the terms are less than equal to m minus 1. So we could write it as m minus
Okay.
1 by
So
2.
good. Okay. So let me mention the argument being given here. So you agree that m by 2 is less than equal to m minus 1. M by 2 plus 1 is also less than equal to m minus 1. All of these quantities are less than equal to m minus 1. Okay? But how many times this m minus 1 is appearing? M minus 1 by 2 times. So what do we get? Let me move this up. Okay, so the claim was that what do we get? We get m plus 2c over m minus 1. Instead of m by 2, we want to say it's less than or equal to m minus 1. The next one also we can do less than or equal to m minus 1. Notice that it's certainly true. It's not only true, it's actually significantly. I mean, we are replacing m by 2 by m minus 1. That's a huge change we are making. Plus m minus 1, plus m minus 1, plus m minus 1. How many times is it appearing? Roughly m by 2 times. Okay? So what is this? M minus 1 times m by 2. Agreed? Okay, what is this? Can somebody simplify this?
It's
C times m.
Yeah. Oh, but that.
So this is equal to m plus c times m. And that's equal to 1 plus c times m. And you might say, oh, that's just a constant, so why don't I take my c to be 1 plus c? But that's the problem. You can't do that. You can't change the constant in your induction step.
So it would be m minus 1 by 2. The number of
I think it's not going to matter. So if you put here m minus 1 by 2,
then it would cancel out.
no, this would cancel with this.
2 would cancel with 2.
2 would cancel with 2. You would get m plus c times m minus 1, which is equal to m 1 plus c minus c, not minus m. And you run into exactly the same problem because this is a small quantity. Okay. Okay. So notice that this is a good example because you have to keep this in mind. But because when you replace m by 2 by m minus 1, what is it trying to say? We are essentially saying that it doesn't matter what the largest size, the thing that we are recursing on might just go from m to m minus 1. But remember, if the thing that we recurse on goes from m down to m minus 1, that is a completely different recurrence, and that recurrence will have a running time of m squared, and you should try to verify it that way. So this would be a pretty significant underestimate of what's going on. Okay, so we're going to stop here. This was just a way of looking at a recurrence that for type we have not seen. But in general, just it's showing you the power of using inductive arguments. Okay? No matter what recurrence you have, any kind of recurrence, if you have a good guess, you can prove that using induction. Absolutely. Okay, with any fine kinds of floors or springs, you can get a completely ironclad proof that that's correct. The biggest challenge in using induction is actually figuring out the guess. And if you're looking at a complex recurrence and you do not know the final solution to it, it's not easy. So you could try to plot it, you could try to run some examples and then look at the plots and then guess what it is and then try to prove it manually. Okay. All right, so we're going to move on and go to our next problem. Yeah, go ahead. Yeah.
I understand mathematically why you say right. I cannot take it as n minus 1 and then 2.
Yeah.
The 1 minus 1 plus. But at the end you say why n minus 1 is wrong and wrong is.
Yes. So recall where this m over 2 plus 1 is coming from. It's coming from that t of m over 2. Where did that m over 2 come from? That was the size of the piece you are recursing on, right? If you're going to replace all of that by m minus 1, then you're saying that when I look at a problem of size m, let me assume that I'm going to recurse from m to m minus 1. If that's what your algorithm is doing, you're recursing from m to m minus 1, that's not going to complete in linear time. It's going to take quadratic. Okay, so let's look at this problem. which is a very good example of a divide and conquer problem. But you will see the motivation for it in many different ways. So let's say the problem I'm given is given n points, and I will explain to you what I mean by points. And imagine these n points are on the board. Okay. So imagine I have put, this is my area, this is the area of the board I'm looking at, and I give you a bunch of points. Okay. These could be like your problem 5 of problem set 2. These could be points on a grid, on a Manhattan grid, or it could be simply points for which, for every point I give you its x coordinate and its y coordinate. Okay, so there are n points. So I give you a bunch of these points. I give you their x coordinates and y coordinates. Okay? For now, don't worry about the fact that, are these real numbers? Are these fixed precision integer? What kind of precision I'm using? Let's not worry about it. Just imagine that these are real numbers, if you will, and I can do any computing on them. Okay? What I want to know is, I give you n points. I want you to find 2 points that are closest among all the different pairs that are possible. Okay? Is the question clear? I give you n points, and I give you those n points in terms of their coordinates, and I want you to find 2 points that are closest. And what's the distance between 2 points? Well, let's assume, in this case, let's assume it's the Euclidean distance. Okay, we can even the Manhattan distance would lead to a similar kind of problem. But let's assume it's the Euclidean distance. The Euclidean distance, if you remember, is simply the distance between these points is what? Square root of x1 minus x2 whole square plus y1 minus y2. Okay. This formula is also not that important. If I give you 2 points, you can assume that there is a black box that will give you the distance. Okay? Is the question clear? Now, questions like these arise many times. Maybe not exactly the same problem, but very similar problems arise many times in data analysis, in large-scale data analysis. You are often clustering points. I mean, clustering is used in almost all machine learning applications. You are trying to analyze some complex data set. You want to be able to arrange the points in a certain way, and you often do a lot of these distance-based calculations in that. Okay? Of course, in many of those cases, it may not be a 2-dimensional point. It might be a 3, 4, 20, 50-dimensional point where each of those dimensions represents some kind of features of points, and each point represents some kind of data point, like a document or a piece of text or some individual who has certain parameters and features. Okay. We are looking at a fairly simple setting. Whatever I'm studying right now, whatever we are going to study right now, you can ask the same question in 3-dimensional, 4-dimension, some fixed dimensions. Once it's really high-dimensional, whatever we are talking about will be very problematic. But as long as it's small-dimensional, many things that I'm talking about will tend to apply. But our question right now is just 2-dimensional. Okay? Is the question clear? I give you these endpoints, and I want you to find the pair that is closest among these endpoints. Okay? Given any 2 points, if you have to calculate the distance, you can simply do this calculation. It will take you 1 unit time. I want you to find the fastest algorithm to solve this problem. Okay? Alright. Whenever you encounter a problem, anytime you encounter a problem in this course, you should try any possibility that you can think of. So, what's the simplest thing you can do in this situation?
Test everyone against every other.
Good. Test everyone against every other one. So, simply, in this picture, if I look at this picture, it's obvious which are the 2 closest points. But you don't have this picture available to you. Okay? All you're given is these set of points. You could say that I'm going to plot all these points and stare at them. But that may be fine for 10 to 12 points, but it's really impossible to do for one. Okay, so I can compare all pairwise distances. How many pairwise distances are there? N choose 2. So that any algorithm like that will take time, k times squared. It will be a correct algorithm, no doubt. So that's absolutely a working algorithm, and there's no problem with that. If that's the best algorithm you can come up with, nothing bad. You have a correct algorithm in place. Of course, the thing is, the question, as always with every problem we will ask ourselves, this is the best we can do. The input itself just gives you, it's just n points. So the input is only of size n, or 2n. So we are taking quadratic. So if n was 1,000, this would be fine, but if n is something like 1,000,000 or 1,000,000,000, this is completely out of question, right? Okay, so can we do better? Okay, so before getting to this, let's try the easier problem. What if these points were in 1 dimension? Okay, and it's always a good thing to, when you're trying to solve a problem in 3 dimensions, first figure out whether you can do it in 2 dimensions. If you're asked in 2 dimensions, first figure out whether you can do it in 1 dimension. Okay, so that's the exercise I would like all of you to open your notebook and try to solve. So I give you n points, and imagine these points are in a line. Note that they are given to you arbitrarily. I give you this point first, second point, third point, fourth point, fifth point, sixth point. So this could be a point number. This could be x1, this could be x2, this could be x3, x4, x5, 6. And I want you to find the closest pair. Okay? I will let you think about it. You have a couple of minutes. You're welcome to discuss amongst yourself if you think. Find the best solution you can to solve the problem. Of course, you can still do this. You can do all pairwise distances, but can you beat this? Is the question. Okay, is the question clear? Any questions about the question? You have a question or you have an answer? Answer. Hold on to the answer. Okay? Try to come up with a method that beats this, and you are just given n points. But you're given only n points, and try to come up, and you're given all the locations. So these are all numbers. This could be 5, 10, 12, 15, 16, whatever. Okay? Okay. So 2 minutes. No, you're given the points. So literally the input you're given could be literally, this could be one of the inputs. It's just one dimension, so there's only one line, right? So you're given, this could be your input. 15, 9, 3, 18, 7, 6, 11, 25, This is your input. So your input is just a sequence of numbers. You can do whatever you want with that input, and your output should be two numbers whose difference is the closest, is the smallest compared to it.
It's a similar question to if you had a set and you want to choose the farthest one.
It's similar. We will look at that.
I think I remember from the book that we like it's crossing. It says
Okay. Anybody wants to? See, somebody who has not spoken before. So, is the question clear? So, I'm looking for answers now. Whatever answers you can think of are fine. You see. There was yes.
So first we can sort this.
Okay.
So that we have n log n complexity.
Okay.
After that, we compare only the adjacent points, the distance between the adjacent points,
Okay.
and the minimum will be the closest square. So that will take n theta n.
So first you sort them so that now you can see them on the line like this. So I told you that the numbers are given to you not necessarily in sorted order. So first you sort them so that this is your first point, this is your second point, this is your third, this is your fourth, this is your fifth, this is your sixth, this is your... Now the point is you really don't need to measure all pairwise distances, you only need to measure adjacent distances. So now that they're in sorted order, you just walk through that array, you look at this difference, then you look at this difference, and you keep a running count of running measure of whichever is the smallest, and output the one that is smallest. Okay? Is that very clear? The running time is the running time of sorting plus a linear pass. That's theta. Okay? So it's very important for you to be able to make such, develop such algorithms using ideas that we have done. Because all we are using here is reduction to sorting, so it's very straightforward. But you should be comfortable in doing that. Now you could ask, is this the best I can do? Is this the best you can do? And it's not entirely clear. This is the best we know how to do it. In certain circumstances we can do better, but this is pretty much the best you can do. And as far as I know, there is no lower bound for sorting. But okay. One of the questions that was asked here was, what if I want to find the distance, the farthest distance? Okay, I will let you think for another minute. And I ask you again, the question is, I give you a set of points like this, and instead of finding the closest pair, I want you to find the farthest pair. Can you do it in n squared? Can you do it in n log n? Of course you can do it in n squared. So people see that everybody should be able to see that you can do this in linear time. Does everybody see that? Just find the largest, find the smallest, subtract them, and you get okay? Okay. Good. So this is just the basics. Now we will try to see whether we can do anything interesting for this. So let's try to apply the same kind of idea. What do? I try to sort them. But what do I sort them on? I could sort them according to the x-axis, but you realize that sorting them according to the x-axis may have no bearing to which are closest. Do people see that? Maybe their 2 points might be far away in the x-axis, but they might be very nearby overall, because the other elements that are quite nearby in the x-axis are really far away in the y-axis. Okay? So for example, So let's see. So what could I do? I could sort according to the x-axis. But then what I might find is 2 points that are very far apart in the x-axis are actually the closest, because the other ones that are nearby in the x-coordinate are in opposite ends of the array or something like that. So one might be here, another is here, then the next point is far down, the next point is far up, and so on. Okay, they're very close in the x-coordinate, but their y-coordinates are widely apart. Similarly, if you just sort according to y-coordinate, that's not useful. Once you sort in one coordinate, then sorting in the other coordinate does not seem to help, because you already are putting some kind of order. So it doesn't seem to. What else could you do? How else could you arrange it? So this is part of the divide and conquer paradigm. Think about, let's try to think divide and conquer.
You can compare it to like the origin relative distance.
Well, that doesn't help, because imagine, notice that the closest pair does not change whether I move things around this way or that way. So the origin could be very far, I don't know. I mean, you can always translate them to close to the
You
origin.
can also calculate the distance.
You can calculate the distance to any point that you want.
So like,
Okay, relative to the median, you could try to calculate the median. Okay, so there was one comment. Yeah.
We could calculate a projection on a line for all the points and then sort it out.
We could calculate the projection on a line. Very good. What line would you choose?
Since it's an x and y axis, we could take a line that passes to the origin, so 45.
Okay, but notice that this is exactly this, right? The sorting according to the x-coordinate is the projection on the x-axis, right? Anything you do, if you translate it like this, imagine whatever bad input I'm giving here, I could give you the same bad input on the projection.
you can have.
Okay, there is one more question. One second.
If you maybe kept subdividing the space into successively smaller squares,
Yeah.
until you get just 2 squares in one space, and see how close those are, and then compare that to what you got from all the other subdivisions.
Okay, good. That's a good idea. We will follow up on that. Yeah.
No, I was saying if you can figure out if there's a line that partitions all the things into half, you can
Good.
find the distance
Okay.
of that line.
Okay. Okay, so we could try doing something like that. So the idea there was partitioning. One suggestion was we will keep partitioning until we find the smallest. One problem with that is you do not know how small these distances are, so you might keep partitioning for a long time, and you do not know where exactly you're going to partition. But that's roughly the idea we're going to explore. So what we're going to do is, let's say this is the board on which the points are. We want to divide it into pieces. Okay. One suggestion was how do we divide it into different squares, but let's do the first part, to the most basic situation. I want to split these things into 2 halves. But my 2 halves have to be such that half the points have to be on one side, half the points have to be on the other side. So literally like Mozart. I want to split that into 2 parts. And I give you a whole bunch of points like that. How do you find out a line that I can draw in the middle so that half the points are on one side, half the points are on the other side? Is the question clear? I want to find, let's say, a y-axis. I want to find a y-axis, a line parallel to the y-axis, so that half of them are on one side, half of them on the other side. Yes?
Use the median of the x-coordinates.
Excellent. Use the median of the x-coordinates. Well, how do I find the median of the x-coordinates? Use selection. Don't sort. Sorting is already, sorting may be okay because we are willing to give up n log n time. But at the moment it seems wasteful. All I need to find is the median. So I would just use selection to find the median. That takes linear time. Okay, so I find the median. Notice that, by the way, the median need not be in the middle of the space. Okay, even though I'm drawing it here, and the actual median line could be here. Half the points could be here, and half the points could be here. Right, that's the median line. The median line is not the median of the possible values. It's the median of the actual x values. Right? So if it turns out that 99% of the points are sitting on this side, then my median line actually will go like this. But that doesn't matter. It's splitting the points into two parts, where half of the points are on one side, half of the points on the other. Okay, everybody see that? Also, for simplification, we're going to assume for now that no 2 points have the same x value and the same y value. It's not a big problem. I can always perturb the points a little bit, or I can even solve it with more care. So for simplicity, let's assume that all the points are on have different x values. Okay, so now what do I do? So what my first? So I didn't do this. I instead find median x squared and split points into two halves. Now what do I do? Remember, pardon? You could, but let me not do it. I've already split them into two parts, and this is the divide and conquer lecture. So what do? I find the shortest pair on the left. I find the shortest pair. Sorry, this closest pair on the left. I find the closest pair on the right. Okay, so far so good. Always divide and conquer. The recursion is easy. What do you do with the recursion is the challenge part. So I find the closest pair here. I find the closest pair here. And maybe in this picture, I don't know. Maybe this looks like the closest pair. In this picture. What's next? So I found the closest pair on this side, I found the closest pair on this side. One would be I just pick the better of the two. What do you think? Is that a good solution? Yeah?
You have to consider the condition when the closest pair is from two sides.
Good. We have to consider the condition. This seems like a reasonable candidate. This one also seems like a reasonable candidate. But we have to consider the condition, the possibility that the closest pair happens to be right close to the line we have drawn. Okay? Everybody with me? Good? Very good. So, okay, find closest pair on left half, closest pair right half, but I have to do the ones in the ones, maybe take 1 point here and take 1 point here as well. Okay? Question?
No, just
okay.
maybe
okay.
anticipation.
So let's try. What could you do? Well, you could choose the best of this, and the pairs that are crossing. How many pairs are there where one point is here, 1 point is here? How many pairs exist with 1 point here, 1 point here? N by 2 whole square. So take best of, let me call it A, B, B, and n by 2 whole square pairs crossing the middle. Okay? This is a good solution. Yeah.
What do you mean by best of?
Best, oh, if you want to find the shortest, closest pair, this gives me a solution of the closest pair. This gives me a solution closest pair. And this gives me n over 2 cross pairs. I want to find the smallest of all, right? Because my goal is to find the closest pair. This tells me that this is the closest pair, this tells me this is the closest pair, and here there are a whole bunch of other closest pairs, other pairs. So I compare all of these, and I pick the smallest of all of them. Okay? Yes?
After that, finding closest pair on both the sides, we can just find the median of the y coordinate and split accordingly, and find another two pairs that are.
Okay, but let's for the moment just hold on. So, is this clear? Is this the correct algorithm? Absolutely, it's a correct algorithm. Is this a good algorithm? Well, again, you should. Well, first of all, let's think about how much work are we doing here? N square over 4. But that's still a lot of work. In fact, it turns out that this is not much better than just trying all the n square pairs. Because you're doing quarter of the pairs you're doing in your conquer step. So if you write down the recurrence for this, you will get a recurrence something like T of n. What recurrence do you get? T of n equals 2t n over 2 plus n square over 4. You solve this recurrence, you already have n square staring at you right there. So this is not going to do better than n square. Okay? So this is the bad idea. The other possible idea suggested was, what if you try to break it into something else? Maybe do a y-axis cut. I'm not going to go over it in the interest of time, but that will also run into similar problems. Okay? So we have to do something more effective in our divide and conquer. Okay, so let's try to make use of. So what is the problem with this algorithm? It's an over 2 square.
Comparing from different points.
It's comparing from different. So you have to compare points here and here for sure. But it seems really wasteful to compare this with this, right? This pair. I mean, look at it. It doesn't make sense. So somehow, can I reduce the number of pairs I'm looking at? That's my question. Find the pairs close to the middle line. Okay, that's a good suggestion. Let's be more precise about it. And let me draw it on this side so that I can hold on to the height. Okay, so let's okay, so now it's going to get interesting. Let's say I find this as my middle line. Okay, I find the closest pair here, and I find the closest pair here, and maybe let me draw a few other pairs. If it turns out that one of these two is really the closest pair, then it's great. But I cannot rule out the fact that there are a lot of candidates sitting here. Okay? So first I want to see, can I prune some of the points? Are there some points I don't even need to look at? Yeah?
You can put a threshold around the region using the two closest pairs that you have found.
Okay. Yeah?
You could like partition it so like you could have like the 1/4 point and the 3/4 and a 4 point? Like the middle path?
Well, let's see. So if I tell you, okay, so let's try to follow that. So 1/4, you mean you take, oh, I see. Got it. You're saying, look at these points, pick a quarter of the points here, and essentially you're saying, let's not look at them.
Yeah, like exclude like the farthest border
Okay.
and the other farthest.
There is a problem with that. What if all of these points happen to be very close to the line? Okay? So in some sense, you cannot simply say that I'm going to throw away some of the points. You'll have to look at the distances. But
Can I calculate the standard deviation from that line?
you could calculate anything you wanted. You could calculate the distribution if you want. Let's try to eliminate based on just the distances. Okay? Which is sort of, instead of looking at the distribution, let's try to eliminate based on the distances. So, what can you say? What points can you safely eliminate from here? Is the question clear? What points on the left I claim I would not need to look at all?
Furthest from the point, the two of
From the, oh, so you're saying I should look at those points that are closer than, those points that are farther from the closest. Everything on the left? Everything on this? I'm not entirely sure of that, because maybe these 2 points are actually quite close here, but then there might be a point here that might be close to a point here. It's not clear. Right? Anybody else? So what points can I safely and surely eliminate? Yeah?
So we know the two distances, shortest distances on both the sides. We take the shorter of them and we'll draw a line from the midpoint on either side and we'll exclude the.
Okay. So let's say this distance was delta 1. This distance is delta 2. And let's say delta is the minimum of delta 1 and delta 2. Then you agree, if I were to draw a line, this delta on this side, delta on this side, I need not look at any points to the left of this and any points to the right of this. It's not entirely clear this is a good idea, or it's certainly not a. All I want to check is whether this is the correct idea. Is it doing the right thing? Is it okay for me to eliminate, as far as pairs? Notice that this is the candidate, viable candidate for my short closest pair. This is the viable candidate for my closest pair. I'm going to take the better of the two, if nothing else. But is it okay for me to eliminate any point on left of this line, saying that it can never be part of a cross pair whose distance is going to be beating the minimum distance?
Because it's more than delta y.
Correct. So notice that this point, if you're looking, if it's a candidate for a cross pair, it's going to be compared with the point here. What's the distance between these 2 points?
More than delta.
Strictly more than delta. So it can never be the closest pair because I already have a delta candidate. So any point less than on this side of the delta line is not a candidate for a good cross pair. I'm not eliminating this distance. Notice that I'm only eliminating these points in this picture from being compared to points here, because I know that their distance is farther away. And similarly, this. Very clear? Okay? Okay. What can I say about the number of cross pairs left? Well, in the worst case, all of these points might be inside this. Right? So, nothing could have changed. So, all of this seems to be not necessarily, will not necessarily work in the worst case. But we are going in the right direction. As you will see in a moment. But is that point clear? Okay? So, what are we doing? So close this pair. Okay, now I'm just writing this algorithm informally right now. So we find median x coordinate. partition, let's call this x10, partition around the line x equals xn, right? That's the straight line, x equals xn. Find delta 1 equals, let's say, find closest pair of left half. Let the closest pair be, let delta 1 be the distance for the closest pair. Find closest pair of the right half. Let delta 2 be the distance for the closest pair on the right half. Now what do? We take the minimum of delta 1 and delta 2. Let delta be the minimum of delta 1 and delta 2. Okay. Now I want to look at, let me call this set A and this set B. So A is the set of points on the left of the line, x equals, it's basically the set of points whose x coordinate is between this point and that value minus delta. Okay? A equals to points with x coordinate in what range? What range are we looking at? X median minus delta to x median. Okay, and B is the set of points with x coordinate x median to x median plus delta. Okay, and maybe B is x median plus delta. Sorry, x median to. Okay, and assume that there is no point sitting on this. Yes.
If would we not be able, once we have the median line, could we not just select like the next element up and the next element down, like one up and one down from the median, and then measure that, and then see if that's more than delta 1 or delta 2?
You could, except remember that the point right next to the median here, closest point might be this one, and the point right next to the median on this side might be this one.
Oh, I see. Okay. Yeah.
Okay. They seem to be very useful candidates to close, but between them the distance is huge. That's the fundamental problem we are facing again and again. That they might be close in the x, and we are only able to sort on one side or the other, and that's what.
Yes. Thank you.
Okay. All right. So now what do we do? Yeah. Yeah. So again, as I said, you can put, since the points are all, they don't have the same anybody have the same x-axis. Imagine the median line as being just to the nothing being there. Okay. And anything that I write here can be, that case can be handled just with a little bit more. Okay. Now, so far that's good. So now we know we only have to compare. We only have to look at these pairs between A and B. Agree? And if we find the best solution for A and B, the closest pair with one point in A, 1 point in B, if that happens to be bigger than delta, then we know one of these two is the closest pair. If that happens to be smaller than delta, then that one would be the closest. Okay? Good. Now is the real crux of the analysis. Okay? Let's do the following. Let me divide this area into exactly half. So this is delta over 2, this is delta over 2. Okay? Yes?
Are we still assuming no x coordinates are repeated?
Yes. Let me split this into exactly half the area, half the space. So delta over 2, delta over 2. Okay? And let me draw this also at distances delta over 2. So I'm tessellating this whole area into square grid cells of size delta over 2. Okay. This is the idea similar to that was mentioned earlier. Why don't we keep tessellating until we find something in a square box? That's something similar to that we are doing right now. Okay. Notice that I'm not doing in the algorithm. I'm just showing you in the picture. Okay, because we can't afford to, because this space could be massive. I mean, you might be given the smallest value could be 0, and the largest value could be like 1 billion. You can't afford to keep breaking this down into cells. We don't do that. But let's look at pictorially what is going on. Okay? Here is the key observation. What the key observation is, so let's look at, so okay, remember, this is the, what is this line? The median line. This is edge delta this side, that's edge delta that side. Each of these is delta over 2, so each square is delta over 2 times delta over 2. First claim I'm going to make, no cell contains more than one point. Can somebody prove why? Is the statement clear? There will never be a situation where a cell looks like this.
That means
May raise your hand. Who has not spoken before? Yeah.
We've already looked at the whole left side and the right side and found that the smallest pair of the two sides was
There was less, was no more than delta.
Yeah.
Sorry, not. The smallest was delta. So if there were 2 points like this, what is their distance? Strictly less than delta. In fact, it's even less than delta over square root 2 or something like that. Right? Yeah, something like that. I mean, even its Manhattan distance is less than delta. So its Euclidean distance is definitely less than delta. Yes?
Can we have skipped a step by, instead of making A and B both offset by delta, just go right to half of delta?
You could. You have to be a little careful. Let me complete this, and then you see that if you try to do it, ignore this completely, you'll be in a little bit of trouble. Okay? And the arguments I'm making, there are some you can make stronger arguments, but they will serve for our purpose. Okay, so you agree that this picture will not occur. All right? Good. That's great. So each cell only has one thing. So if this is the picture that looks like to you, and I tell you that this cell is occupied, this cell is occupied, this cell is occupied, this cell is occupied, this cell is in this picture. So far I have said that I don't have to worry about these points comparing with those points. So there's no, I don't worry about this. Can I look at this picture and eliminate some pairs? Just looking at the picture. Which pairs can I eliminate? Can I eliminate this pair? Why not?
You can.
Why cannot I not eliminate this pair? Because the distance could be delta over 2, right? You don't know. What about this pair? Well, I'm not even looking at that pair because I'm only looking at cross pairs. This pair is already taken care of, right? Okay. Okay, but I cannot eliminate this pair. Can I eliminate this pair? Yes. For sure. I don't need to look at it at all. Okay. So let me focus my attention on this point, which is sitting in this cell. It's the only occupier of that cell. Okay? Any question?
No.
No. How many cells should I, for that point, how many cells should I bother looking at?
3.
Are you sure?
8, actually.
Okay, so give me a number. As long as it's the correct number, if it's a large number, that's fine. But so let's see. Do I have to worry about this cell? Yes. I've not shown you a point here, but there could be a point here. I have to look at this cell. What about this cell? What about this cell? Yes. This could be sitting at this corner. There could be a point sitting at this corner. Right? Then their distance would be delta over 2. Okay? So I'll have to look at this. What about this cell? No, because even if this was coming to this corner and this was coming to this corner, the distance will exceed delta. Okay? What about this one? Yes. Yes. Because the distance between these two is... No, that's not true. Yeah. This we don't need to. No. This is delta over 2, this is delta over 2. So the distance between this is less than delta over 2. So this I should look at. This I should look at. This I should look at. So, and similarly, this I should look at, this I should look at, this I should look at. Right? So for this thing, I have to look at 10 cells. At most. Guaranteed no more than 10 cells. Is that very clear? This is really the crux of the argument. And you can actually be with a more careful analysis, like we hinted there, you can probably reduce this from 10 to something else. But for now, 10 is, we are happy with 10. What about this one? How many cells I have to look at? At most 10. At most 10%. What about this one? Probably less than 10, right? Yeah. Because this is already followed. But you agree that for any point, I have to look at most 10 cells. Question?
So for that, the box you just pointed out,
yeah.
The one that's not next to the median, why do we have to look at any point? I think except for maybe if there was the only choice I could think of is like if there's a point on the other side, basically on the edge of the box.
Not necessarily. Imagine there is a point sitting here. So let's take a look at that point. We certainly have to compare with this because there might be a point sitting here. There could even be a point sitting here, which would be a candidate.
That would be.
Yeah, because its distance would be this. Remember, this is delta over 2.
Right.
So this cell is a candidate. Even this is a candidate.
Right.
Actually, even this is a candidate. Right? So there are a few. Maybe not as many as 10, but there are a few candidates. Okay. So for each point, we are out of time, but let me just say the following. For each point, there are at most 10 candidates. Okay? So the key idea is going to be, notice that we do not know which cells are occupied, but we can sort all the points according to the y coordinate. And for each point here, we only have to look at some 10 of points on the other side. 5 on this side, 5 on this side, or something. So that's what we're going to do. We're going to sort all the points according to the y coordinate. And then, just like in the linear scan, we only compared with our neighbor. Here we are only going to look at 10 points around us. Then we will finish it off. Okay. Stop now.